It's live now, but I need to share the link somehow.
That's grand.
Oh, come on. Share. Okay. Copy link. And then go to Facebook, I think. Facebook. Oh, come on. Let me do what I want to do.
Where should the link be?
What are you talking about?
For people, like I'm on the XLC project working group.
It's in both the comments, your one and my one.
Comments, okay.
Yeah.
Oh yeah.
It's there. It's there. Go ahead. Although.
Okay.
Yeah, there's some people who've joined now. There's some people have joined the class. There's 6 people in the class at the moment.
Right. So
8.
Anyone who was in my class the other day, we were talking about that in probability when you do experiments, they assume that things are fair. So if you toss a coin, they assume that there's no problem with the coin and you're equal to get a heads as a tail. So what I'm going to look at first of all is looking at probabilities from experiments. So the first one I want to do is imagine if you think that there might be something wrong with the coin. So it might have damage on it that makes it lands on heads more or makes it lands on tails more. So you can do an experiment to see, is the coin biased? And what you do is you toss the coin, say 200 times, and then you record the number of heads after 10, after 50, after 150, after 100, after 150, after 200 tosses, and see, you should get roughly 50% heads and 50% tails. And if you don't, if that number's off, then it can show you the relative frequency, if it's right, if it's wrong. Now I'm just going to show you this example here. So you tell me if that's what that needs to be.
Which example? This one?
The top one, the
top
coin.
One. Okay. Yeah.
Okay, so you see there, we had the number of tosses 10 and you got the number of heads of 7, and then your heads divided by your tosses gives you the probability of how many heads are coming up. So to get the relative frequency then of a number, the estimated probability that event would happen, the relative frequency is the number of successful trials divided by the total number of trials. And that will give you the relative frequency of something happening. Okay, so this is an experiment. If you're doing more than one experiment, then you keep a record of the more than one experiment that you're doing. Okay, so the next thing that I want to have a look at is when events are not mutually exclusive. So when up until now we have been doing, for example, that you'll get things will only be counted once, so they might be counted more than one time. So what we're going to look at these events. So let's have a look at this example here. This one. Okay, so you have the cards 1, 3, 4, 5, 6, 8, 9, and 11. So if you're asked what's the probability of a red card or an even number. So there are 3 red cards and there are 3 even numbers. So first of all, the probability that it's not a red card plus the probability that it's an even number. For example, it's not 3 over 8 plus 3 over 8 as the number 4 is counted twice, but you don't want the number 4 counted twice. There are only 5 red cards or even numbers. So you have the probability of a red card or an even number is 5 over 8. So because there's that red card, that red card, that red card, you don't count that even number, you count that even number and that even number. So you get 1, 2, 3, 4, 5. So you don't count the red 4 twice. You make sure you don't count it twice. Okay, so the sort of general rule, like you can do that through logic, through just using common sense and knowing that you don't count the same thing twice. Or the way you do it is you get the probability of A or B. That's the probability of two events. The way you do it is you get the probability of one event. So in this case, the probability of a red card is 3. You get the probability of the second event, which is the probability of the even card. In this was, you had the 4, the 6, and the 8, so it was also 3. And then once you have those two probabilities, you take away the probability of any overlap. So you take away the probability that the card would be red and even. And the probability that card would be red and even is 1. So you take the 1 away and that leaves you with your 5. Okay, so that's what you do when they're mutually exclusive. So when you can't use the same number twice, basically. Okay, so what we're going to look at now is a quick, and this will be a real refresher from your junior cert, is looking at Venn diagrams and the use of Venn diagrams in probability. So to remind you what a Venn diagram is, it is two circles that intersect or come together.
2 or more.
Okay? So that's a very basic Venn diagram.
Lovely.
Okay, we add on to that, and that very often a Venn diagram is inside a rectangle, right?
Universal set. Wonderful.
Okay. And the rectangle represents something that is not in either of the circles. So let's have an example so you know what we're talking about. So let us take this one. So the Venn diagram shows the sports played by members of a club. So you want to know how many members played both football and tennis but not football, neither of these two games, football or tennis. So we have our football circle and we have our tennis circle. And then we have information that's just belonging to football, that's just belonging to tennis, that's belonging to both, and information that is outside. So that's what our Venn diagram looks like with the information represented on it.
Mm-hmm.
Okay, so hold on to the copy there. So point to how many members played both football and tennis, right? So we have 10, which is the number that encompasses both circles, where the two circles intersect, and that's the people who played both football and tennis. So who are the people who played tennis but not football? Your answer should be 35. That's the one that's on its own. Who played neither of these two games? And that's where your universal set comes in. That's the number that's outside of the circles and in the rectangle. Who played football or tennis?
$85 people.
Yes.
I'm brilliant at this.
So the football or tennis, you add your 40, you add your 35, and you add your 10 to get the people who played basically both sports. Okay, so now what they want you to do is write down the
either of the two sports.
Yeah.
Not both sports. Both sports is 10.
Yeah. So now what they want you to do is write down the probability of each of the above. So what is the probability that you have both football and tennis? Now remember I was saying in class the other day, in order to do probability, you need to know what your total is, right? So the first thing you have to do is you have to add up the total number of people that are there. Now, the mistake people often make here is they add the 40, the 10, the 35, and the 45, okay? But what you have to understand is that 10 that's in the middle, just make sure you don't add it on twice. On that some people add the 40 plus the 10 in the middle, the 35 plus the 10 in the middle, and the 45. So what you want are all the people who play football, which is the 40 plus the 10, so that's 50. You then add in the tennis people, so there you're 35, so you're up to 85. And then you want your people who don't play any sports at all, that's your 45. So that brings you up to 130. Okay, so your total number is 130. So all your probabilities are going to be written as a fraction over 130. So then once you've written them as a fraction, so for example, both football and tennis will be 10 out of 130. But make sure you just reduce it down to its smallest fraction. So 10 out of 130 is 1 over 13. Okay?
And you can do that if you put it into your calculator.
Yeah,
top divided by bottom, the calculator will give you the smallest fraction possible.
Your calculator will do that for you. We have a calculator.
And some questions require it as a decimal as well. So just press the SD button.
Yeah. So if you want it as a decimal, change it into decimal. Sometimes you need it as a percentage as well. So again, just change it into percentage. You remember in class the other day, I was writing it as a fraction, as a decimal, and as a percentage. So make sure you check on the question what it asks you to do, whether it asks you to do it as a percentage, as a decimal, or leave it as a fraction. But definitely, if you're leaving it as a fraction, make sure you've reduced it down to its smallest fraction. Okay, so then sometimes what you have to do is you have to fill in the Venn diagram. So you're just given the information and you have to build the Venn diagram. The common mistake there is figuring out the number in the middle, all right? When you're filling out the Venn diagram, just be careful doing the number in the middle. Let's give you an example.
Now, while we're doing that, I'll quickly answer Thomas's question.
Yeah.
I think it was Thomas. What's in the fridge is loads and loads of toilet paper and hand sanitizer. Just so we're clear. Very important.
Okay, so in a class of 30 students, we have 8 studying music. We have 14 study art, 6 study both music and art, and so represent this on a Venn diagram. So you start out by drawing your Venn diagram, your rectangle with your 2 circles, okay? And then you're going to work out who plays what. So the first thing to do is to fill in the bit in the middle, okay? Who plays both? So the people who play both, 6 play both music and art. So 6 are going to go into the middle part of your Venn diagram, right? So that's the people who do both music and art. Now, out of your class of 30, 8 people study music. Now remember, you've already counted for 6 of those in your who does both. Who does both. So what you want is what's left that only do music. So if 8 altogether do music and 6 of those 8 do art as well, then you're left with 2 that do only music, and that goes in the music circle. Then you have your art. 8 study music, 14 study art. So you have 14 study art. You've already counted for 6 of them. Okay, so you want what's left out of your people who study art. So you take your 6 out of your 14, and you should be, hopefully, if my maths is right, left with 8.
Yeah.
We good? Okay. So we have the 8 that study music and the 14 that study art. Now, does that account for all 30 of our students? Is the next question that you have to ask yourself. And you'll know if you add 8 and 14 that does not give you 30. So the remainder of the class goes outside into your box. So what's the remainder of your class? If you have 14 and 8, that gives you 22 out of the 30. So you have 8 left that study neither. He's checking to see if it's right first.
It's not though.
Why is it not?
10 plus 14 is 24.
Oh, well, 24, so 6 then. 6 that do neither. Where are you getting your 10 from?
Wait a second.
It's
There's
8 and 4.
How many in the class?
30.
Well, these numbers add up to make 24. Because of 6, 2, 8, and 8 is 24.
8, and that's right. You do 62, you're 8, so you have more than that left over.
14.
So it's 14 outside.
Who don't do it? If those order numbers are correct.
Yeah. Well, music is 8, art is 14, with 6 that do both. That's your Venn diagram. Okay. So the thing to be careful of is the overlapping number, right? Make sure that you don't count those twice. And then when you're working out your probability, once you have your Venn diagram worked out, then writing probability is just a case of looking at it and seeing what you've left to do and all that sort of stuff. Okay, so let's have a look at the multiplication rule, okay? Or sometimes it's known as the, I don't know how you pronounce it, Bernoulli trials? Something like that. Okay, so very often with these, you start out by a sample space. So just have a quick look at just that thing there, and then I'll go through it.
There's that thing there.
Right.
Coins, dice, heads, tails, 1 to 6, and then the combinations possible. Yeah. That enough?
Yeah. Right, so you've drawn out your sample space. You have your heads and your tails. You have your dice 1 to 6. So from the sample space, we can see that the probability of getting a heads and a 6 is 1 over 12. Okay, whether or not the coin lands on heads has no effect on whether the dice shows a 6 or any other source. So the two events, rolling the dice and tossing a coin, are completely independent. Okay, so the probability of getting a head when you toss the coin is 1 over 2. It's a half. Half the time it's going to be a head, half the time it's going to be a tail. The probability of getting a 2 on the dice is 1 out of 6. Okay, because there are 6 numbers on the dice, so one of them is a 2. So it's a 1 out of 6 probability. So if we multiply the two probabilities together, so let's say, I mean with this, right, if you're doing a heads and a dice, it's probably easy to work out the sample space. But let's say you have 2 events that are just too enormous to work out a sample space, then this will work. You multiply, you get your 2 probabilities independently of each other, and then you multiply them together. So if we multiply the 2 probabilities, which is your 1 over 2, multiplied by your 1 over 6, okay, then what you get is your 1 over 12, which is the probability that we got of getting a heads and a 6. Okay, so the rule is, let me sort of hold that up rather than me writing out what's already there, that the multiplication rule, okay, that with 2 probabilities, if you're getting probability A multiplied by probability B, see the first of all they're in the same bracket, then you just multiply the 2 probabilities together. Get the first probability, get the second probability, and multiply your 2 probabilities together. Okay? Mm-hmm. Mm-hmm.
Should probably just wear gloves altogether when we're handling that book. Gotta be careful.
Okay. Now, a common question that I've seen come up where you would use this is very often with 2 people that have birthdays, right? So if you say, for example, find the probability that you have, say, Mary's birthday falls on a Monday. Okay, well then your probability is, so we'll do this. So Mary and John have their probabilities in the same week. Find the probability. Birthdays. What I say? Probabilities.
Yeah.
Their birthdays in the same week. So find the probability that, number one, Mary's birthday falls on a Monday.
1 in 7. Easy.
Well, there's 7 days of the week, so your total is 7. She's only going to have a birthday on one of those days, so it's 1 out of 7. Okay?
Yeah.
Find the probabilities that both have their birthdays on a Monday. So both have their birthdays on a Monday. So you have, first of all, Mary is 1 out of 7. You've figured that out as well. John is also 1 out of 7. So you multiply the two of those together and you get the probability is 1 out of 49. Okay, so the next question, find the probability that both birthdays are on a Saturday or a Sunday. Okay, so at the weekend. So the probability of Mary having a birthday on Saturday or Sunday is 2 out of 7. The probability of John having a birthday on a Saturday or Sunday is also 2 out of 7. So you multiply the two of those together and you get 4 out of 49. Okay, so multiplying fractions, you multiply the two top numbers together and you multiply the two bottom numbers together to get your answer. Okay, so the next things to have a look at are what are called tree diagrams. That's the proper name for them. I always call them spider diagrams because I think they look like spider webs, but they're called tree diagrams. So this is where you have a probability and you're working it out. So of say 2 or more events. So let's take, for example, a group of people, although not right now, are going to the cinema and they're also going for dinner beforehand and, we'll take those two. So cinema and dinner. So in the dinner, they have, when they're deciding where to go for dinner, they have a choice of 3 restaurants that they can go to. So we'll call them McDonald's.
I knew you were going to say
that. Burger King and Supermax.
Classy.
So we have M, B, and S for McDonald's, Burger King, and Supermax. Okay, and then the 2 films that they can choose between. Let's say they're choosing between 2 films, and we pick like some banging films here now. So they can choose between Insidious,
or Pride and
which
Prejudice,
we'll call with an I, or The Conjuring, which we represent with the letter C.
That's a hard choice.
So let's start first of all with the restaurant choices. So you put down your McDonald's, your Burger King, and your Supermax. Keep them well spaced out. Is that seeable from there? Or do you need
Not really. Yeah, you get the idea. So there they are.
Yeah, we'll take our time with
That's
this one.
supposed to be an M. There's so many typos in this, it's weird.
Okay, so if you go to McDonald's, you then have a choice of 2 films afterwards, of Insidious or The Conjuring. So you can choose to go to McDonald's and then go to Insidious, or you can choose to go to McDonald's and then go see The Conjuring, or you can choose to go to Burger King and go to see Insidious, and Burger King and go see The Conjuring, or you can choose to go to Supermax and then see Insidious, and you can choose to go to Supermax and then see The Conjuring. And that is a very basic first sort of level of I can nearly call it a spider diagram, a tree diagram. Now, when you go to the cinema, you can have the choice of either getting popcorn, which you represent with a P, or ice cream, which I'm not going to use because I have an eye already, popcorn or nachos, or a hot dog. So we've P, N, or H. So you could go to McDonald's, go to see Insidious, and while you're there, you could order popcorn, or you could order nachos, or you could order a hot dog. Or you could go to The Conjuring and get popcorn, nachos, or a hot dog. Okay?
Jesus.
So that's your McDonald's choice. And as you can see, our tree diagram is getting more complicated now.
Yeah.
So, and you have the same option with each. Every time you make one slightly different choice, it's a new combination. It's a new thing you've done. So you could have gone to Burger King, gone to see Insidious and ordered popcorn, ordered nachos, or ordered hot dogs. Or you could have gone to Conjuring and got popcorn, nachos, or hot dogs. Your other set of choices is you could have gone to Supermax, then gone to see Insidious and ordered popcorn, nachos, or hot dogs, or gone to The Conjuring and done popcorn, nachos, or hot dogs. So, how many total options do you have? So if you count those up there and say, point how many options you have. So you count up, you just add up how many at the
6,
end.
9, 12, 15, 18 different possibilities of your night out.
Okay, and because every choice is a different choice. Now that's doing with a tree diagram. You can also say you have 3 choices of restaurants. You have 2 choices of cinema, and you have 3 choices of snack.
More typos.
Yeah. Okay, so you can put each of your choices down as a number and multiply them together, and you will get the same answer in the end. Okay, now Owen.
So the probability from that, though, the probability of watching Insidious.
Yeah, so your probability of going to McDonald's, watching Insidious, and having a snack, any snack, would be 3 out of 18. So you use that then to work out your probability. Now Owen is going to hold this up and go through this example with you. Just read it, go through it from the book.
I don't know this example. Huh?
Okay, so a box A contains red beads and blue beads. A box B contains 2 red beads and 3 blue beads. So 1 bead is taken at random from each box. So first of all, draw a tree diagram to show all the outcomes. So you have your box A and your box B, okay? And so you have your red or blue in box A, and you have your red or blue in box B. So you can, from box A, pick a red, and then from box B, you can pick a red or a blue. From box A, you can pick a blue, and from box B, you can pick a red or a blue. So your outcomes are red, 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 blue, blue, red, or blue, blue. And again, to get the probabilities, you multiply your probabilities together. So if box A contains 3 red and 4 blue, then the probability of getting a red is 3 out of 7. So the probability of getting a red from box A and a red from box B is 3 out of 7 multiplied by 2 out of 5, which gives you 6 out of 35. So it's similar to what we were doing, where you do the 2 probabilities independently and you multiply them together to get your total answer. Yeah. Okay, and they are tree diagrams. Now, do you want to keep going, or is that an awful lot for one class? Not keep going? I think we're going to stop there because that's an awful lot of material. See, the thing about it is when we're not stopping for you to do examples yourself, we're getting through an awful lot of stuff very quickly, and that's not necessarily ideal. So what I'm going to do next is I'm going to take some photographs of some of the exercises from this book and just post them on the thread so that you can have a practice of doing one or two of these yourself. Okay, so I'm going to put those straight up now. So for the last quarter of an hour or so, I'll tell you which numbers to do and have a go of them yourself. So I'm going to give you like sort of one exercise from each topic that we covered. Okay?
Over and out. We shall do another broadcast of a math class tomorrow.
Very soon.
Tomorrow. Okay, goodbye. Patreon. Oh, there's comments that came in.
All right.
That I hadn't even seen. Oh well.
Were they?
Oops.
She can always address them on Facebook.
Yeah, I'll address them in person, I think. I'll just read out some of them anyway. So we have, what's in your fridge? Got that. Cleaning your hands every time you touch the book. We're Patreon, yeah. Hope you're all staying safe during the epidemic. Anyone with a spare pen. And so on. 1 out of 7. Yeah, I got that right. 2 out of 49. Oh, here's a good sum. COVID 20 minus COVID 1 equals COVID 19. Yep. Add or multiply. Yeah. Okay. Right, we'll leave it there anyway. Right. See you again. See you tomorrow. I think that's it. How do you end this thing? Press the X, maybe? I think it's press the X.